software engineer at Joyent, where I primarily work on Node.js and libuv. And my talk today is called Out of the Box Node.js Diagnostics. So just by a show of hands, who in here is running Node.js in production? Who in here was running Node.js in production like 4 or 5 years ago? So it used to be really hard back in the old days to get diagnostics information out of Node. Node was kind of built with a small core philosophy where the idea was that the core of the project would remain as small as possible, and little things like getting diagnostics information would be pushed out into the NPM ecosystem, and that left us with modules like Node Inspector, Node Heap Dump, Long John, and a variety of other ones. But then as Node kind of matured and enterprises continued to adopt Node, we realized that it was kind of a pain, and we kind of needed to have these things built into the project. So over the past few years, a lot of work has actually gone into this area. I don't think a lot of people who aren't involved with the project day to day are aware of it, so I wanted to kind of give this talk to try to get the word out. And instead of having to npm install a bunch of modules and then go in and edit your source code, add signal handlers and things like that, usually you can just have Node, Chrome, pass some command line flags, and then you're good to go. So I wanted to start with one of the older diagnostics features that was built into Node, the debug environment variables. So basically, there are 2 environment variables that you can use to print out information from Node either in the JavaScript layer or the C++ layer. Those variables are NoDebug and NoDebug native. And all you do is, as you start up your Node process, you pass in a comma-separated list of subsystems that you'd like to see extra diagnostics information from. So the example I have here is we're setting NoDebug is equal to net and HTTP2, and then starting our server. I have a project that uses HTTP2, so I ran my test suite with this, and you'll start seeing a lot of things printed like this. So it's not necessarily important for you to understand what is being printed here, because this is just an example, but you can kind of see that there are HTTP2 sessions being established, connections that are being dropped, and things of that nature. And if you're interested in seeing, what all is available, you can browse through the Node source code. The subsystems kind of line up with the file names. So if you go into the Node core repo, look under the lib directory, you can see like libnet.js, and you'll be able to search and see all of the things that you're seeing here. And so it's a good way to, without modifying your code at all, see what's going on underneath the hood. And then a few years ago, we introduced the concept of warnings into Node. So these are things that we're going to print a message for if you're doing something that we think might be a little bit dangerous. Things like making TLS connections that are not secure, using deprecated features, things like that. You can turn them off if they get on your nerves with the -- no warnings flag. I wouldn't recommend that, though. If you're seeing a lot of warnings and it's just too much in your console, you can actually redirect them to a file with the -- redirect warnings flag. And then the more interesting one is -- trace warnings, which will actually, whenever you encounter a warning, it'll give you a stack trace showing where in your application that's coming from. So an example is just a one-line require sys. Sys is from years ago. It's a deprecated module in Node Core. I don't think anyone's still using it. You shouldn't be. But if you run this example here, you'll see, without any command line flags, you'll see deprecation warning, sys is deprecated, use util instead. That's good and all, but it doesn't really tell you where in your application things are coming from. But if you add the -- trace warnings in front of that, you now get this nice stack trace, and then the red arrow that I have here shows you where exactly in your code base that call is coming from. Then similar to warnings, we have a special class of warnings called deprecations. So these are just features that we no longer advise people to use in production. And we have a set of flags that work pretty similarly as warnings. So -- no deprecations. I imagine if you've seen the buffer constructor deprecation, a lot of people have turned that one off. I still don't think you should do that though. -- trace deprecation works similarly to trace warnings, but is special cased only to deprecation warnings. And then deprecations, you can actually cause your application to throw if someone's using a deprecated feature. That's probably something you want to do more in development, not necessarily in production, but -- throw deprecation is there for you. And then just going back to the same one-liner from before, now I'm using -- throw deprecation and running the same code, and then you see basically the same warning is printed. There's the same red arrow showing you where in your code it's coming from. And then one nice feature that has been introduced in the newer versions of Node, whenever you see stack traces like this, I'm not sure if you can tell on the screens like this, but the stack frames are actually different colors. So up where it says deprecation warning, that's in black text, and then it changes gray for a while. Those are internal things or things that aren't necessarily your application code. And then the line with the red arrow is back in black again, kind of signifying this is your code, this is where you're doing something that you probably shouldn't be. Next is talking about Synchronous I/O. So this is one of the best ways to introduce performance problems into your code is by using Synchronous I/O. Now, if you're working on a server application, it's usually fine to have some initialization period where you're first starting up the server, but you're not listening in server traffic yet. But once you start actually serving requests, you don't want to be blocking the event loop. You'll run into problems very quickly. So we have the -- trace sync IO flag that will actually show you warnings with stack traces of where you're using synchronous IO so that you can get rid of it. And so an example here, again with a one-liner. I don't know why anybody would do this, require FS, and then read the actual file that the code is in, and then not do anything with the results. But it's just a demo. So what you see here is we're doing read file sync. Now, if we didn't have the set immediate around it, everything would be fine because this would be happening in the first event loop tick. But because we're using set immediate, that defers until the next tick, and so you'll actually be using synchronous IO whenever you shouldn't be. And because read file actually does a few things under the hood, not just opening a file, but it opens, does a stat call, reads the file, and then closes it, you'll actually see a number of these here, and it kind of gives you more visibility into why you shouldn't be doing this in the first place, because that's a lot of trips between Node all the way down into the libuv event loop and back that you should probably be avoiding in production. Next up is a newer feature. I think it came out in Node 12 for dealing with unhandled promise rejections. So everyone has probably seen the warning. I forget the exact text. Something Node is going to start unhandled rejections are deprecated. Node's going to start throwing or something like that. And a lot of people complained about that because not handling promise rejection is perfectly fine. It's behavior that's in the JavaScript spec. But that behavior was kind of defined with browsers in mind and not so much with servers. So if you have an unhandled rejection in the browser, chances are it might impact your experience and you might not even be able to tell. But if you have an unhandled rejection in the server, that's just asking for things like file descriptor leaks and other things because your code stops progressing, and if you had a file that you had opened, that's now staying open. So you definitely want to avoid these in server contexts. If you're using Node for things like command line applications, it's not quite as big of a deal. But you can now pass the -- unhandled rejections flag, and it has 3 modes of operation. You can kind of specify how you want to handle them. So strict mode is it's going to throw an unhandled or an uncaught exception every time it runs into one of these. That's my preferred way to deal with unhandled rejections. Another alternative is if you just want to have a warning printed, you can use that with the warning option. And then none goes back to the default standard operation of just swallowing all the unhandled rejections. So another one-liner here, we're just calling promise.reject and passing in a new error object. And since we passed unhandled rejections equals strict from the command line, it's actually going to throw an uncaught exception. Another reason that the uncaught exception or the strict option is nice is because you can now integrate your promises code with your existing unhandled rejections workflow if you have one. So things like process dot or abort on uncaught exception. So for years now, V8 has been shipping with something called the tick processor. This is a profiler. It's kind of a two-step process. So you can actually profile your code as it's running. It's going to dump some file that's not really meant to be consumed by humans. And then you would do a post-process step to kind of take that and then format into something that people can read. So an example would be if you're running your server node-prof server.js, that's going to get you a file. It's going to be isolate-0x and then a whole bunch of numbers, -v8.log. And then you would run node again afterwards, node-prof process, and then the name of that file. And you'll see some output like this. There's a lot going on here. So I had to truncate the output because it just wouldn't all fit on a slide. But basically what this is showing you is where you're spending time in shared libraries, so things that aren't even part of your application necessarily, where you're spending time in JavaScript, and then where you're spending time in C++ code. And then there's another section that wouldn't fit on the slide that kind of is a summary section breaking down Node or JavaScript versus C++, et cetera. So I encourage you to play with that. An interesting thing here about the JavaScript section, if you look, it says the lazy compile and then the asterisk process immediate internal timers line. The asterisk means that V8 was actually able to optimize your code. So if you don't see that, then there's a chance that your code is not optimized and you might be spending more time in there than you realized. And then a couple years ago, the folks at V8 were kind enough to integrate dev tools basically directly into V8 so that we had access to them in Node. And so that lets you do things like have access to a step debugger without having to go and install the Node inspector module. There are a couple ways that you can start it. One is --inspect. That's basically going to start the inspector, but nothing else. It'll just be kind of hanging out in the background. And then you can pass in a port and a host that you want it to listen on because you're going to be connecting to that later. So by default, it'll connect to 127.0.0.1 port 9229. We actually had a security issue a couple years back. We were originally binding to 0.0.0.0, which is basically all the interfaces. So if you're running in production over the internet and somebody had the right IP address, they could technically connect to your server and start debugging your application for you. So that was bad. We changed that. And then the other way that is a lot of times more useful when you're doing local development is with --inspect break. So that takes the same options for host and port as the inspect flag, but it'll actually put a breakpoint directly, like as soon as Node starts up, so that you can actually go in and do any type of setup that you want without having to try to catch breakpoints in your code at runtime. So this is just an example of what it might look like. Node --inspect break example. You'll see a message printed to the console. It's saying the debugger is listening on, and then a WS : that's a WebSockets URL. That's how these things actually communicate. And then a nice message that directs you to the Node documentation so that you understand what you're trying to do here. And then you can use dev tools. You can connect to that, and then you'll see just a basic. If anyone that's seen Chrome dev tools before, this is the exact same thing. So you can step through your code, profile it, and things of that nature. And that's leading me into CPU profiling. So one of the things that's always been a little bit awkward inside of DevTools was getting your server set up and then going in and trying to start up a CPU profiling session. And then you have this awkward period where you're trying to then kill the server and you're applying load, and it's just a lot of weird timing things. So we actually added flags built directly into Node where you can do --CPU prof, and that will start the CPU profiler, and then when Node exits, it will write a CPU profile output to a file. And then you can specify using the CPU prof dir and CPU prof name what directory you want to write that to and what you want the name of the file to be. If you don't specify it, it'll get dumped to your present working directory, and it'll be some long file name that's like a combination of the date and some other things. So if you care about like fancy file names, that you want to use those. You can also set the CPU prof interval flag, which is how often the sampling profiler is going to sample your application. By default, it is 1 millisecond, I believe. And then, of course, you can do this in DevTools if you really wanted to. So this is what a CPU profile kind of looks like. It actually goes off the bottom of the screen here because this is, the stack trace is just too big to fit on a slide. But what you're seeing here is the top section is showing you kind of a high-level view over time of what the CPU activity is, and then you can actually select windows inside of that, and it'll show you a more detailed breakdown down below. And an important thing to notice here is that in the top area, the timeline doesn't quite line up with the bottom, so the top is your overall picture, whereas the bottom is anything that you've zoomed in on. And if you can read this, which you probably can't if you're sitting in the back, you basically see that you're doing some requires here, and that's where the big spike in CPU activity is coming from. So that'll help you diagnose a lot of performance issues, but another common thing inside of Node is, or JavaScript in general, are memory leaks, and those usually come from things like closures, you're keeping references to objects that you no longer care about, but you still have a reference in your code somewhere, so the garbage collector can't actually go in and release the memory. Back in the old days, we would use the Node heap dump module, and then you would go in, you would add a signal handler, so you could send a signal to your application, and it would dump a heap snapshot for you. Now we have this built-in heap snapshot signal flag, so you can now send, as many signals as you want to Node. It'll dump these heap snapshots, and then Chrome DevTools actually has a nice built-in way that you can compare snapshots across, this snapshot versus that snapshot, and you can kind of identify what objects are in memory, and helps you like narrow down where a leak might be. So this is what a heap snapshot looks like in Chrome DevTools at a very high level. Basically, the list on the far left is every type of object that's in the JavaScript heap, and then you can actually expand those, and you can look at every single individual object, and you can actually see the path to what other objects are keeping references to that, because that's going to be what's going to be the cause of your memory leak. And then on the far right side, you'll see columns that say the objects count. That's basically how many of these things are in memory. The shallow size, which is going to be the size of this object itself in memory, and then the retained size, which is generally what you're going to want to look for in leaks. The retained size is, I have this object, how many references to other things in memory am I holding by having this object still? And if you can kind of read that at the top, it says you have this object that's holding on to over 3 megs of memory. So that might be something you'd want to look into if you're diagnosing a memory leak. Another new thing from the V8 team is asynchronous stack traces. So if you've ever done anything in Node where you do like set timeout or any asynchronous operation, that basically breaks your stack trace, because the things that were on the stack at the time that you initiated this asynchronous operation are no longer on the stack anymore. So it makes it really hard to debug, because you can see that there's an error, and you can see kind of a few stack frames, but you can't really tell where. If there's 100 different call sites in your application, you can't know for sure which one is causing the problem. And there was a module that was pretty popular called Long John over the years, and it would stitch these asynchronous stack traces together, but that came with a lot of performance overhead, so you couldn't really do it in production. The VA team found a way with async await code that you could actually have no cost or low cost asynchronous stack traces, and so they'll show you where the stack, where the asynchronous operation boundaries kind of are. Unfortunately, it only applies to async and await code, and from my experience with it, it seems to involve adding some extra awaits into your code that wouldn't normally be necessary. So I'm not going to include an example of it in here, because I'm unsure of just how great it really is at this moment. But here's an example where we're basically calling a function called foo. Foo does a set immediate operation to queue up an asynchronous operation, and then that's just going to call bar. And if you look at the stack trace that you get back, you see the error and you see bar, but there's not really any sign of foo. Inside of DevTools, though, they use the old-fashioned, like, high overhead, not want to do this in production method of stitching the stacks together. And so you can actually see with the red arrow that it is there. So at least if you're debugging in DevTools, you do get the asynchronous stack traces all the time. Tracing is something that's been around in Node for a little while, but has gotten more attention over the years. So you can do -- trace events enabled, and it'll actually output various events that happen inside a node. These might be in V8. These might be things like accessing the file system, performance-related things, async hooks, things of that nature. You can configure which of those things you want to see by using the trace events category flag. Users can actually also create their own trace events, and you can use them to see how long an operation takes. And then inside of Chrome, you go to Chrome://tracing, and you'll see a view like this. And so I think my cursor was lost in this screenshot, but if you look down at the bottom, you'll see fs.sync.read. So this is actually a file system read operation. You can see that I read 546 bytes. You can see when it started, how long it took, and things like that. So it's pretty useful for seeing what's going on inside of your code. In recent versions of Node, we also added TLS Connection Tracing. So if you've ever wondered why I can connect to this server, but as soon as I try to do it over HTTPS, it doesn't work. And then you might have been directed to use the OpenSSL command line tool, and then you have to kind of extract that out of your code, and it's just more of a headache. But now you can just pass -- trace TLS, and you'll get a whole load of debugging information just printed to the console every time you try to do a TLS connection. And then you can actually set these. That'll set the flag will work for all the connections in your application. You can do it on a per server or a per socket instance if you really want to. And then JavaScript recently added, or V8 added code coverage. So the old way of doing code coverage was kind of clunky. You would have to, if you've ever tried to do step debugging through old code coverage code, you would be stepping through all these really ugly lines of counters and things that didn't look anything like your source code. And then they would have to actually update their way of doing this every time they added new language features, so it just kind of lagged behind. V8 now does that for you natively, and then Node can also piggyback off that with the Node_V8_coverage environment variable. That will actually be the name of a directory where you want to write coverage information. Now, the coverage information that comes out of V8 is like a JSON format that you're not going to really understand if you look at yourself. But there are nice tools like C8, and right here I have an example of using C8 with MPX. So it's just a one-liner running this code, and you can actually see that because we call node example with no other arguments on the command line, the output is did not get the foo arg, and then C8 will actually dump out a list of all the files, the statements, the branches, things that are covered, and things of that nature. And then there are ways that you can go in and you can actually get more detailed views. So you can pull up a file and you can actually look line by line and see where there's coverage or where things are missing. Postmortem debugging is another way of getting information out of Node. This one has been around for a long time, because back from the days of when Joyent was running the project, because they're big users of postmortem debugging. The problem with postmortem debugging is it's got a pretty high barrier to entry. So you have to go in, you have to set up your system to collect core files. Core files are basically an exact snapshot of an application when it crashes. They're turned off by default on most operating systems because the core files get quite large. So you have to enable that, and then you would run node with -- abort on uncaught exception. And then once you get this core file, you can analyze it with a tool like llnode, which gives you pretty deep insights into stack frames across the JavaScript and C++ boundaries, which most tools don't give you that type of visibility. And then you can inspect JavaScript objects and a lot of other really cool things. Another problem with this approach is that tools like llnode depend very heavily on the internals of V8, and so they break every time Node upgrades a version of V8. So we're always playing a sort of game of catch-up there. And so that kind of led to another recent addition in Node, which are diagnostic reports. So this is, I like to think of it as a very lightweight postmortem debugging. You don't get all of the same detail of information that you would get with a core file, but there's a much lower barrier to entry, and it's much more configurable. So you can generate a diagnostic report on, on a signal, or if on a crash, on an uncaught exception, and then there are actually programmatic APIs inside of Node. So you can do process.report.getReport, and you'll get a nice JSON object with all this information. And it includes things about the system, the Node process, things that are going on inside of libuv underneath, the C++ stack, and just a whole bunch of other good things. Unfortunately, it is still experimental, but because it's not code that's going to really impact your running application, I would recommend using it. I'm a big fan of it. And to configure it, there are a handful of flags that you would use. So because it's still experimental, you would have to turn on -- experimental report just to enable it at all. And then if you're interested in collecting information when Node crashes in the C++ layer, you would use -- report on fatal error. If you're interested in uncaught JavaScript exceptions, there's -- report on uncaught exception. There's the -- report on signal. So if you want to send a specific signal to your process and have it generate this report, you can do that as well. And then you actually define which signal you want to use with the -- report -signal. I believe by default it uses SIGUSER2 for that. And then the report directory and report file name just lets you specify where you want to write these reports to. Like I think I said about the heap snapshots, by default you're going to get it's going to be a file name that's based on like the year, the date, and a bunch of other stuff. And then this is a kind of a truncated view of what one of these reports contains, but it's a giant JSON object, and it tells you things like, in this example, you can see the event was the JavaScript API. I called this myself from inside a JavaScript code. The trigger is getReport, so that was me calling process.report.getReport. If you had an unhandled exception or something like that, that line would be different. And then it has timestamps, process ID, like the command line flags that you started. And then it just, I definitely recommend looking into it because I can't show everything on this slide, but it's really cool stuff. And that is all that I have. So thank you for coming to my talk.
Thank you. Thank you very much, Colin. So 2 questions. For beginners and people who have never really profiled systems, what is one tip you'd give them in getting like their feet wet in using profilers for V8?
One tip I would give. Oh, it's a tough one.
Or like how'd you get started with system profiling and this sort of stuff?
So I was working in the Happy.js ecosystem. There was a memory leak inside of Lab, the test runner. And so I went in and was collecting heap snapshots and comparing them to see why all these tests were leaking memory so much. And it actually came down to domains.
Oh, domains, wow.
Yeah.
What would you like to see in the sort of profiling systems evolution? What tools would you like to, oh my God, this would be so cool?
What I would love to see, and what I think there's actually some work being done on, is I was talking about postmortem debugging and how it breaks with every upgrade to V8, an API to basically eliminate that breakage every time. So if the V8 upgrades just automatically kept working with postmortem debugging, that would be awesome.
I agree, that would be awesome. Thank you so much, Colin.
Thank you.